All right, so last time we went up to talk about, where were we? The limit of a function. Before we get to that, actually, I wanted to take a step back. I kind of glossed over this a little too. I would say I glossed over this section a little too much, because I actually want to go kind of deeper into this topic, the tangent and velocity problem. So I mean, I said that later on we'll talk about velocity and how it's used in physics. It's like, yeah, it's like the classic application of calculus, right? Is the birth of like a lot more science that came out, physics, things like that. Okay, but really understanding such a classic example will help us sort of develop this theory as we go on as well. Okay. Well, why is that? Well, it's because this has a more intuitive sort of idea when we think about it, but later on when the math starts getting a little more complicated, we're using this idea, but we're sort of assuming that you remember this, how it's like actually applied in real life. Okay, so we'll see more like real world problems, such as like rate of change and things like that, where we have to convert between units and things like that. And it's going to be useful to understand the physical applications, such as velocity and what it means to be tangent. Okay, so in this section, we will see how limits arise when we attempt to find tangent to a curve, the velocity of an object. Okay, so the tangent problem. The word tangent is derived from the Latin word tangens. Sorry, I don't speak Latin. Not sure if that's correct. Which means touching. Thus, a tangent to a curve is a line that touches the curve. In other words, a tangent line should have the same direction as the curve at the point of contact. How can this idea be made precise? Okay, so let's see. So in other words, a tangent line should have the same direction as the curve at the point of contact. That sounds way more complicated than what it is. Look here, if you see in figure 1b, this red line represents what the slope is at P. This is point P on the graph. Looks like the function is called C. This is the curve called C. And so this line is exactly what's being described here. This is a tangent line at the point P, meaning this line only touches this curve precisely at this point in this region, right? We see that it crosses here as well, and that happens from time to time, but focus your attention right here. This part of the graph they're only touching at one singular point, okay? So let's see. Okay, for a circle, we could simply follow Euclid and say that a tangent line is a line that intersects a circle once and only once, as in figure 1a, as I was just describing. This is how it's introduced in geometry. What it means for a line to be tangent to a shape. Well, it only intersects at one point then. Okay, let's see. For more complicated curves, this definition is inadequate. Figure 1b shows two lines L and T passing through a point P on a curve C. The line L intersects C only once, but it certainly doesn't look like what we think of as a tangent. The line T, on the other hand, looks like a tangent, but it intersects C twice. Okay, so that's a great point. I sort of alluded to it when I was bringing it up. This line, what this paragraph just stated basically is that this line may seem inadequate, or the definition that we know that a line that passes through a circle once is tangent. Well, if that's the same for curves, well, it's not true that it only hits it once, right? It hits it at P. This line hits this at P, and it also hits it here. So using that definition from geometry, we can't just say for circles it's the same for curves, because it's going to intersect it twice. That being said, though, this is still a significant line. This is still the slope at P. So you kind of have to think about, we need to take away these global statements such as a line intersects a circle once means that it's tangent. That's a global statement. Well, it's global when we say that all curves follow this this notion. So what we need to be more specific about is think about what it's like locally or around the point. Around this point, the line only hits this function once. And that's significant, like I said before. That is tangent at the point P. There's no other tangent lines. Okay, So that's a huge point. It's a super huge point. So we go through the classic example of a parabola in example 1. Find an equation of a line tangent to the parabola y equals x squared at the point P, 1, 1. Okay, so let's work through this solution together. So we will be able to find an equation of the tangent line T as soon as we know its slope m. Okay, so that's really all that it is. In order to find the equation of a line, right? This is using some skills from algebra, such as finding slope and also finding a point, and knowing what information is able to be drawn out from the given situation, right? We're given just a parabola y equals x squared and a point 1, 1. So of course we want to know slope. We want to know slope and point. Together we can use the point slope formula. All right, so let's see. So if we were gonna draw, so y equals x squared. And by the way, my first video I did describe sort of a lot of the skills that you're gonna need in order to understand what I'm doing. So that being said, if there's any point that you don't understand, just don't be afraid to write a comment. I can sort of explain it. Okay, so we have y equals x squared. We should know how to graph this. It doesn't have to be a perfect graph, obviously. I'm freehanding this. So here's a rough, shaky sketch of x squared. And we also have a point 1, 1. So let's say this is 1, 1. Okay, here's P. That's what they called it. All right, so we need to be able to find an equation of a line that's tangent to the point at that point to the graph y equals x squared. So what do we do here? Well, okay, let's see. How will I know that a line will hit the point P? Like there's gonna be only one slope, which makes that true. So let's see how the book does it here. Okay, so if we choose a nearby point x squared on the parabola, and we figure out, okay, so all right, awesome. So I'm looking ahead and it looks like, yeah, we're using the idea of a limit here. Yes, okay. Wow, all right, interesting. Yeah, so essentially what we're doing is we're calculating slopes from the right side. So we say this is some point x squared, right? The function is x squared, so if I plug in x, I do get x squared out. And what we do is we're finding slopes of lines that connect those 2 points. The job here is to get x. So right, let's say like this point was actually to the right of 1. So if I plugged in 2, then I'll get 4. Then I have a line. I have a line connecting these 2 points to 4 and 1, 1. Well, that's 4 minus 1 over 2 minus 1. Oops, 1, which is 3 over 1, which is a slope of 3. So from a point from x equals 1 to the point x equals 2 on the parabola, the slope that connects those 2 points is 3. Okay, we want to minimize, right, for the fact that the line's going to intersect the line twice. We want it only to intersect once. What do we do in that situation? Well, we're gonna calculate x values that get closer and closer to 3. Oops, sorry, not 3, 1. And we want to do this, right? If I look at a close-up image of this is a piece of the quadratic where this is 1, 1. And I want to make x get smaller and smaller, or closer and closer to 1. So I can pick values like 2. So x equals 2, x equals 1/2, x equals 0, 1.005. So I'm just choosing numbers that get closer and closer to 1. Last time we talked about sequences. So this is sort of, you have to think of this as a sequence of points from the right of x equals 1. Okay, we're sliding that to the point over the point P at 1, 1. So we not only do that from the right, we also do that from the left. And as we calculate the slopes of the points of these intermediate points, such as from 1, 1 to 1.05, and also from radially from the left, right, 0.05, then, or 0, or 0.95, right? Then what you'll notice is the limiting slopes, or the limiting factor slope. So the slope from the top, slope from positive side is the same from the negative side. Okay, so the slopes, so if I draw a little picture, the slopes that are approaching this way, so these lines are going to be approaching the same slopes as coming from the left side. And the point that ends up being on the point itself, right? When I actually connect the 2 points, you're going to have a line that only intersects the graph at one point and only one point. Okay, so why did we do all this? Well, it was just sort of to work through a mental image of what exactly it means to find the slope of a curve, or a tangent line to a curve. Okay, we have to look at a local, we have to look at this object locally, meaning I'm only thinking about what's happening near that point. Okay, this is sort of the basic foundation of analysis and using infinity in order to understand these topics. Okay, but again, this seems more complicated than what it actually is, so I fair warning for that. We're going to talk about what's called the derivative, which is exactly what this is. The derivative is going to be the slope of any curve at a point. Okay, we're going to find ways to mathematically prove what some of those theorems entail when it comes to derivatives. Okay, moving on. Super important process, or super important concept. And again, it's used in physics, which is, can't lie, it's not the reason why I like doing this. So these problems are very useful, and we're gonna see more of them in the future, so I'm just gonna avoid them now. Okay, so that's kind of gonna be the basic principle of when we're understanding the limit of a function, all right?